is almost my talk already. So thank you very much for the introduction. I would like to thank, sorry. Oh, I did not press that button. Okay. I would like to thank the program committee for inviting me to this fantastic conference. I would like to thank the organizing committee for the organization, and I would like to thank you for staying up all the way to the last talk, the last presentation before the B-Boys. And I will report today on Einstein-Podolsky-Rosen entanglement in Bose-Einstein condensates. And the results that we have obtained in our experimental group in Hanover were obtained in a collaboration with our theory colleagues, Luis Santos and Clemens Hammerer in Hanover. Also theory, Luca Petze and Augustus Merzi in Florence, and also Jan Alt in Aarhus. So in our experiments, we employ Bose-Einstein condensates that we prepare in the state F equals 1, MF equals 0, and then we wait for collisions to happen where two atoms in 0 collide and produce a pair of atoms in plus minus 1. And this pair is entangled just in the same way as entangling photons works in optical parametric down conversion. Here, a strong coherent pump beam enters a nonlinear crystal and produces pairs of photons in the signal and idler mode, which are also entangled. So these entangled photons represent the entangled atoms in our case. In our preliminary work, we could show that this process is a possible path to amplify vacuum fluctuations. We could produce twin Fock states for interferometry beyond the standard quantum limit. We could create many particle entanglement and squeezing beyond 10 dB, and an interaction-free measurement based on the quantum Zeno effect that played a role in the last talk in our latest result. But we're not the only ones that are using this process based on a lot of early work, starting with pioneering work by Wolfgang Ketterle. Now there are some groups employing this, exactly this process to create non-classical states, including Mike Chapman, Dan Stamper-Kern, Markus Oberthaler, and now also Li Yu. And today I will focus on two results of our group, which is the creation of continuous variable EPR correlations and the application of this type of entanglement for improving a microwave clock. Okay, so let's go back to the very original proposal of Einstein-Podolsky and Rosen in 1935. Here they devised a source of a particle pair with strongly correlated position and momentum observables. So if you measure the position of particle A, you can precisely predict the position of particle B. And the same holds true for the momentum. If you measure the momentum, you can predict the momentum of particle B. And so these precise predictions seemingly violate the Heisenberg uncertainty principle. So they concluded that a measurement of the system A must change the quantum mechanical system state of particle B. So if you want to create these strong correlations of continuous variables in an experiment, you will for sure not create these very strong correlations with exact predictions, so you have to quantify this a little bit. And so I would like to introduce these prediction variants that scale how well you can predict system B from system A. And then you can set up two criteria. The first is the EPR criterion, which applies when the variance product of these two variances falls below the value of 1/4. And this is a very strong criterion because it is much smaller than the classical threshold, which is set at 1. And then there's a weaker criterion, the inseparability criterion, which says that the sum of these two variances must be below 2. Both of these criteria have been fulfilled in optics experiments, starting with this famous experiment by Wu et al. From 1992. And here they actually employed optical parametric down conversion to create the entanglement that is needed. But they did not measure real position and momentum, but they measured the x and p quadratures, but they are equivalent observables as they are continuous and satisfy the same commutation relation. So you can set up exactly the same criteria for this. Since then, many optics experiments have both demonstrated this sum criterion and the product criterion in many experiments, and I copied this from a review of modern physics from 2009. And since 2009, much more experiments demonstrated this strong type of entanglement, and with ever-increasing records. But can you do this also with massive particles? And here you see an implementation with atoms, and that has been obtained in the group of Eugene Polsik by quantum non-demolition measurements. And this is only the first paper of a series of papers where they could obtain this strong type of continuous variable entanglement. Later in the group of Markus Oberthaler, it was also possible in a system that is very similar to ours to demonstrate this type of entanglement. However, both processes were only shown to demonstrate the inseparability criterion, but not the stronger type of EPR entanglement. Okay, so this is the outline of my talk. I will introduce you to our experimental setup. Then I will show you the experimental results, and I will present you that we can fully reconstruct our many particle state. And finally, I will come to an application for precision measurements. Okay, how do we engineer these strong correlations? We do it exactly in the same way as the optics people do. In optics, they operate optical parametric down conversion to create a two-mode squeeze state in these signal and idler beams, leaving the nonlinear crystal. And then they have these strong correlations in the quadratures. And quadratures can be measured by such a homodynamic setup. So they send the signal and idler beams to such a beam splitter where they mix it with a strong coherent state, the local oscillator. And by now choosing a certain phase of this local oscillator, they can choose which quadrature is to be measured. And then the final measurement is performed by an intensity measurement of the two output ports. We now follow the exact same setup. So we start with our Bose-Einstein condensate in the state f equals 1, mf equals 0. We wait for collisions to happen to create the same two-mode squeezed vacuum state in mf plus 1 and mf minus 1. Then we shift one of the levels to tune the phase of our Bose-Einstein condensate in mf0, which takes the role of the local oscillator. And now we perform atomic homodynaming by applying a radio frequency pulse which couples our local oscillator to both the plus 1 state and the minus 1 state. And by choosing this phase, we can choose whether we want to record the x or the p quadrature in our two spin modes. And then the intensity measurement finally is a measurement of the particle number in all three modes. So how does it look like? We create our Bose-Einstein condensate in a cross-beam optical dipole trap. We apply a very stable magnetic field. Then we prepare our rubidium atoms in the state f equals 1, mf equals 0. Then we apply a waiting phase where we wait for collisions to create this two-mode squeezed vacuum state. So this creation process is easily described by this Hamiltonian, which just describes the creation of particle pairs in plus minus 1 or the annihilation of pairs in plus and minus 1. And if you apply this Hamiltonian to empty modes in the beginning, you will create this two-mode squeezed vacuum state, which is just a superposition of twin Fock states. So either 0 particles in plus 1 and minus 1, or 1 particle and 1 particle, or 2 particles and 2 particles. And by engineering the waiting time, we can adjust the squeezing factor and the mean number of atoms in this state. Okay, after the creation of the state, we want to record the correlations in the quadratures. We apply now a radio frequency pulse, which couples to these two modes. And then finally, we want to measure the atom number. We switch off our chap. We expand the three Zeeman components in an inhomogeneous magnetic field. And then we use standard absorption imaging to count the number of atoms. Okay, what do the results look like? This is now a typical histogram that we record. Now, we record the X quadrature by choosing the appropriate phase. And this is now the quadrature in the +1 mode called XA, and this is the quadrature in the B mode, XB. And you see that we have very nice anti-correlations between these two quadratures. And now we can predict precisely the outcome of a measurement in B by measuring A. And the quality of this prediction is quantified by this small variance in this direction, which is exactly the prediction variance that I introduced in the beginning. Now we can tune the phase of our local oscillator to a different phase. And now you see that we have a nice correlation in the P quadrature. And we again have a nice prediction variance in this direction. Of course, we cannot tune our phase only to two values, to X and P, but to any phase value in between. And then we expect histograms for the two-mode squeeze state, which look like this. And here you see the experimental results. On the X-axis, there are different local oscillator phases. On the Y-axis, I have the prediction variances. And you see that they follow a nice sinusoidal behavior. And they reach both well below the vacuum noise limit. And at these two minimum positions, we identify the phases with the X and the P quadrature. And now we can evaluate, of course, the two criteria by multiplying and adding these two variances. This is the multiplication. And you see that, indeed, our values reach well below the EPR threshold of 1/4 by 2.4 standard deviations. We can also record the sum of the two variances. Here we go well below the inseparability criterion, and we even reach this area here, which is sufficient for EPR entanglement. So this is the first time these continuous variable EPR correlations with massive particles have been obtained. But I would also like to refer to related work on Bell correlations in the BSC, which was following a theoretical proposal by the ICFO group, and Maciek Levenstein is in the audience. And the experimental realization was in Basel in the group by Philipp Treutlein. Okay, now we can use all this obtained data to do a full state reconstruction. Remember that each of these points here is one of these histograms, and now we can set up a four-dimensional density matrix and play with all the different ingredients to reproduce these marginal distributions. This is the result of an ideal two-mode squeeze state, and this is now the result that we obtain by a maximum likelihood analysis. And if we do this, we get a very nice density matrix. Of course, I cannot plot all four dimensions. This is the number of atoms in the A mode. This is the number of atoms in the B mode. And this is now a really clean two-mode squeeze state, because you see that the strongest component is here the vacuum state, and then the single particle twin Fock state, here the two-particle twin Fock state, and so on. Of course, we also have here these off-diagonal parts which are unwanted, but we can reduce them mostly to the effect of the finite sampling. So if we had much more measurement data, we could suppress them even further. Okay, now we would like to apply this type of entanglement that we created for quantum metrology, and in effect we have now realized a prototype of a microwave clock. So how do classical microwave clocks work? I have sketched here a Ramsey sequence for a microwave clock, and for a classical clock you typically input all the atoms in one of the two input modes. Then you split them onto the two modes where they acquire a phase shift, and then finally you mix them again and you operate your clock typically where the two output ports are symmetrically populated. So in fact, this classical scheme acts as one big beam splitter where all the atoms that are input are split onto the two output ports. So that means that this is effectively, again, a homodyning detection, and so the noise of the output reflects the noise of the quantum vacuum input over here. So this gives rise to the standard quantum limit, the shot noise limit, which allows only a certain precision for the estimation of this phase. Now, if you want to go below the standard quantum limit, you have to employ entanglement, and one easy way is to just apply a squeezing operator to this vacuum input. And this has the advantage that you can keep your more or less classical state over here, and you just apply a little bit of squeezing here. This is opposed to most other approaches which have been demonstrated in the literature, where the two input states are more or less symmetrically populated, and I have listed some of the groups that have performed measurements in this direction. The only exemption, perhaps, is interferometry with W states, where you input a single Fock state over here, which has been described in a previous talk by Jakob Reichel, and has also been performed in the group of Vladan Vuletic. Okay, but we would like to explore now this vacuum squeezing, and this is interesting, and I would like to show you an example from the optics community. This is the Gravitational Wave Observatory at GU 600 in Hanover. This is a huge laser interferometer with a 600-meter arm length in both directions, operated with 12 watts of laser power. And of course, if you would like to do measurements beyond the standard quantum limit, you would never dare to send these 12 watts of laser power into a nonlinear crystal. On the other hand, they can apply vacuum squeezing to create a single mode squeezed vacuum state, and then they send the single mode squeezed vacuum state of really just very little power into the empty vacuum input. And thereby they achieved and operate now on a regular basis this huge interferometer beyond the standard quantum limit. Okay, we would like to do the same thing, and I showed you in the previous part of the talk that we can create this two-mode squeezed vacuum state. And now we just can create single-mode squeezed vacuum by a basis change. So we now go from the states +1 and -1 to a symmetric superposition of +1 and -1. And this means that we evaluate these squeezing quadratures along the diagonal directions. And then we convert easily our two-mode squeezed state into a single-mode squeezed state in the symmetric state. Now we can use this single-mode squeezed vacuum state for interferometry. So here's the standard level structure of rubidium. Normally, a rubidium atom clock is operated between the two clock states, F equals 1, MF equals 0, and F equals 2, MF equals 0. And now we replace the lower state here by using this symmetric superposition state instead of the standard clock state. Nevertheless, this state is also a nice clock state, as it is insensitive to magnetic fields to first order. Now we perform standard Ramsey interferometry, obtain nice Ramsey fringes, which allow us to measure a microwave frequency with precision. And now we set ourselves to this mid-fringe position to investigate our phase resolution. And this is now a zoom in into this mid-fringe position at 0.5 transferred fraction. And now we evaluate the noise of our system, and we deduce a phase estimation uncertainty. And here we reach a value of approximately -2 dB. Although this value is not extremely large, it nevertheless represents the first application of squeezed vacuum for atom interferometry. And I still think it's very nice to see that we operate an atomic clock with 10,000 atoms, and the signal is improved by the application of squeezed vacuum with a mean of 1.5 or 0.75 atoms. Okay, this brings me to the end. I would like to summarize that I have shown you continuous variable EPR correlations in the Bose-Einstein condensate. I showed you that we are able to fully reconstruct our many particle state, and I have shown a proof of principle application of this squeezed vacuum to a microwave clock, and we believe that this here can indeed be a viable path to employ squeezing for precision interferometry because all the noise that you see in the results are all limited by really technical noise. And we explore this path together with Ernst Rasel in Hanover. So I would like to thank my collaborators in Hanover, and I would like to acknowledge support by our newly established Quantum Metrology Center, DQMAT, and I would like to thank you for your attention.
So we'll have some questions.
Yeah, nice talk, Carsten. Could you explain a little bit what you do theoretically, experimentally, to prepare the M equals 0 state with your basis rotation, your superposition?
How I prepare
what you do concretely in the clock operation?
Ah, yes.
So the actual experimental
Yes, I was
sequence.
very short on this. I apologize. So in principle, we start. So now I explain first only the classical clock, yeah, without squeezing. So we start with our Bose-Einstein condensate in the state f equals 1, mf equals 0. And then we apply a radio frequency pulse, and a radio frequency pulse only couples to the symmetric state. So that means that we can prepare half of our atoms in +1 and -1 in the symmetric superposition. This acts as our phase reference. Now we apply a microwave pulse, which transfers all remaining atoms up to the upper clock state, wait for a certain Ramsey time, then we bring it back down. This is the Ramsey time. Bring it back down. And now we close the interferometer by applying another radio frequency pulse. And this is now our signal. We now relate the number of atoms in +1 and -1 to the number of atoms in 0. And at first it seems like a complicated thing, but actually it's a quite nice sequence because now we can evaluate also the number of atoms in +1 and -1 relative to each other. And we get in parallel a signal of the magnetic field because these states are now really sensitive to magnetic fields. So we get a clock signal and a magnetic field signal at the same time.
Thank you.
If there is no more questions, it's time to close the section. Let's thanks to all the speakers again.
Yeah.
Okay, that concludes the conference. But there is one final entertainment that Won-Ho Jae prepared. That's Korean B-boys. So, okay, these guys are called